Statistical mechanics here is understood as the classical statistical mechanics of Gibbs with probability distribution, which is where beta is the inverse temperature for canonical distribution, but interestingly, in this particular case, we do need to also discuss microcanonical distributions, where the probability is just constant density on or constant distribution over the constant energy hypersurface. So normally we don't care, but in this case, perhaps we will. Star clusters here simply means a large collection of stars, and stars here are Newtonian, in our approximation, Newtonian point particles. And the question mark is here because this statistical mechanics, sometimes it works, sometimes it doesn't, but mostly because there is a question which I cannot answer here, and at some point I thought I can answer it. So it works funny, this statistical mechanics, so much so that I'm planning to do some numerical simulations of this, and my hope is that one of you will tell me why I should not, that it's all trivial and I should not waste my time. I tried asking Shura Grossberg and he referred me to some experts. The reply of those experts was, we cannot help you, but this can be understood, of course, in the sense you are so far gone. So anyway, we will see. So there is something I don't understand here. Okay, so the plan of the talk is, first I will give you a quick introduction into classical statistical mechanics of Newtonian particles. Then I will describe astrophysical applications, because it is those astrophysical applications which allow me to describe this discuss this very old theory. These applications go back mostly to Tremaine, but also his collaborator Tuma. I will call this Tuma-Tremaine thermodynamics. To me, this was presented by Levin, who recently wrote another paper on applications of this statistical mechanics of star clusters. And because of Levin's interest, he convinced us to work on it, and we did some paper with Levin and Zhu, Jerome, our graduate student. So it will partially be based on this thing.
And that's still Levin at Columbia.
Levin at Columbia, Yuri Levin. So after I discuss this astrophysics, I will describe what exactly can be done in this paper, because one of the results of this paper leads to my question, which I would want you to answer if you can. And assuming you cannot answer this, I will tell you about how I am going to proceed to answering this question, and maybe you will join me, because I'm planning some very concrete numerical simulations, because after all, it is classical statistical mechanics. Classical statistical mechanics, in some cases, you can run on your computer. And so I am actually going to run it on my computer, but not for stars, for some simplified system, which I will describe. In case somebody gets interested and wants to run it on his computer, and then we can compare results. Maybe we will understand something this way. Okay, so intro, which perhaps will be the most interesting part for most of you, because it is simple, beautiful, not mine, and everybody should know it and appreciate it. So, intro into classical statistical mechanics, I will ask two questions. Does it thermalize? And if it does thermalize, what does it thermalize to? Let's start with the simplest possible collection of stars, some globular cluster perhaps. of a given size, given mass of a star, number of stars n. Then I have fully described the system and stars of mass m within distance r. Question, how long will it take the stars to thermalize? The stars, of course, thermalize by colliding with each other, right? For the collision to be efficient in deflecting those stars, the stars should pass at a distance such that so B here will be the impact parameter. The stars should pass at a distance such that the resulting energy is of order kinetic energy. And since my system is V-realized, kinetic energy of a star, typical kinetic energy of a star, is its typical binding energy in the whole cluster.
You're
right?
just assuming it's serialized.
Yeah, I'm assuming it's serialized.
It might be
It
not
should be,
thermalized.
if I wanted
Okay.
to thermalize, it should start by V-realizing, right? Then by comparing these two numbers, these two quantities, you see immediately that the typical impact parameter for scattering, gravitational scattering, is the size of this thing divided by n. So they should, if there are 1,000 stars, they should pass at a distance the size of this thing over 1,000. How long should you wait before you pass at such a small impact parameter is of course easy to compute. The mean free path here will be of order concentration times sigma. Concentration is total number of stars over r cubed. Sigma is impact parameter squared, the cross section. What's that? No, that's fine. So this little star should cross this system n times before it collides once. So thermalization time is dynamical time multiplied by the number of stars. Immediate conclusion, galaxy, for example, if I take elliptical galaxy, if I get dark matter, put all those stars, galaxy, the crossing time, perhaps it crosses the entire galaxy like 100 times per Hubble, but the total number of stars there is whatever, 100 billion. So a lot, yes. So it will not thermalize. On the other hand, globular cluster near its center will have a much smaller crossing time, and the number of stars near the core of the globular cluster can be as small as 1,000, perhaps, whatever you call a core. Okay? So this thing then does have a chance to thermalize, and it kind of starts thermalizing, whatever. So yeah, there are self-gravitating systems which might be close to thermalized. Okay? So what will be this thermal state?
So can I have a
Sure.
simple question? Most of the visible matter in galaxies is gas and not stars, and then there will be dark matter. But
Most visible matter is gas.
visible.
Is it? It depends on what distances you are talking about. Like at
So
10,
indeed, I mean, my question is, in this case, why you don't take into account dark matter and gas?
because at this point I'm just talking about some theoretical background. What do we expect from self-gravitating systems? I'm not yet discussing anything real. We will pass to real systems in a second.
But in the
Right.
real thermalized things, gas is irrelevant.
Yeah, for a globular, there's still gas that are.
Right.
I mean,
But even in the galaxy, I don't know this, like within our 10 kiloparsec, is it, I would say probably it is mostly stars, not gas. Gas is
in our galaxy, yeah.
in our galaxy, right? So, okay, but again, I'm just talking simple theoretical introductions here, yeah.
Is there mean free path increases as I add more objects to the system?
Mean free path increases as you add more objects to this system.
Right, at fixed
if
size,
you-
I add more objects to mean free path. I get it comes out
right,
as canceling.
right.
Is there an intuition for why that seems backwards?
Good point. In fact, we had very similar discussion with Marcus about plasmas. They have similar property, counterintuitive kind of. Because remember, what do I keep constant here? If you keep constant R and constant M, and you add more stars, then the stupid things start running faster. And if you run faster, you should pass even closer in order to get deflected. So these things are kind of counterintuitive. Good point. All right. So sometimes they will thermalize. What will be the result of this thermalization?
To have like a lump, all of them.
Say again?
Why don't we expect them to be collide into one like superstar?
We shall see what will happen. So I said, if we wait long enough, they will thermalize. Now question what they will thermalize into. If I have molecules in this room, I know how to describe them. They have this probability, and then to compute thermodynamics, I can compute partition function. Let me compute partition function for just two particles. One will be fixed, another at a distance r and velocity v. Then my partition function here will become integral of phase space, e to minus beta, and energy here will be minus 1 over r plus v squared over 2, and I'm dropping dimension full quantities whenever I wish. Okay? This is the gravitational potential, this is kinetic energy, this is energy, e to minus beta e is the Boltzmann factor, this is my partition function, all thermodynamics will follow from it. One look at this integral, and you diverge both at 0 and at infinity. You diverge at 0 because here your binding energy is minus infinity, Boltzmann factor is infinite. This is algebraically small for small r, but this is exponentially large for small r. This wins over this, partition function diverges at 0. Likewise, it diverges at infinity. If I go to large r, this grows algebraically, this saturates to constant, okay? So my partition function here is infinite. How do you interpret this infinity? It's quite clear, but let me step back a little bit. Okay, wonderful. So this is infinite, but what about?
Can I ask a question about the previous thing you talked about?
Yeah, sure, absolutely.
So I thought it was true that in these systems, actually, the collisions are dominated by the long range, the
This is
distant
true.
collisions.
This is true.
And
This
not the
is
short
called
range.
Coulomb logarithm. Indeed, the question was this: in the self-gravitating systems, I wanted my collision to get me, of course, his attraction, to get me scattering by angle over the unity. In fact, there will be, since I'm dealing with long-range forces, far-away collisions which scatter you much less, however, will be way more frequent. Indeed, it will logarithmically diverge, but who cares about logarithms?
They might be pretty large.
In this case, they are
They
over
have
the
the
10.
finite size.
They are, in this case, indeed, they are over the 10. So indeed, for globular
pretty
clusters,
large for
it
a
does
logarithm.
matter, in fact. This 10 does matter because, yeah, sure.
Even the
But,
10's a big one.
but who cares how they thermalize if it doesn't work anyway, okay? So you can say, okay, so this doesn't work, but maybe microcanonical will work. And indeed, if you do this for two particles, this surface indeed will have finite. This is a finite surface indeed, right? But of course, I hope you recognize this is partition function for microcanonical distribution. But of course, you realize that I'm talking trivialities here. Sure, what is microcanonical distribution? It means you are on a surface of constant energy, right? But constant energy for two particles, the energy of an ellipse is just its semi-major axis, right? Remember these things from Keplerian dynamics. Semi-major axis fully defines the energy of the orbit, okay? So the fact, if I keep to keep the energy of an orbiting particle constant means to keep the semi-major axis constant. But the space of constant semi-major axis is of course compact, and therefore microcanonical thing will converge. However, the minute I go to more particles, this will be the distance between particles, this will be individual velocities, then I can do the following. I can take two particles very close to each other. For this, I will pay the penalty of r cubed. But once I have two particles very close to each other, my kinetic energy, which will be 1 over r. If it is kinetic energy of many particles here, of n particles, the corresponding volume in velocity space, right, the volume of the sphere with n coordinates and radius r, grows as this thing to the power n. So microcanonical distribution does not save you if you on a constant energy hypersurface, but you have like 10 stars, it will be infinite area of this hypersurface, which of course is to be expected. This is all in perfect agreement with our physics intuition. Sure, if you let the stars be, they will collect into tight binaries, and they will eject other stars. Those things have infinite phase volume, okay? Because there is a lot of room at infinity, and there is a lot of room here in terms of energy, okay? So, sure, these systems don't thermalize. And it is signaled by the divergent partition function.
Is that equivalent, Andrei, to the statement that if it radiates energy, it gets more kinetic energy? Like there was this problem in the bathroom a while ago that if a gravitating system releases energy, it gets higher in kinetic energy. Is that the same statement or is that a different statement?
Well, only here, in fact, we will get back to it. Only here, of course, the processes are non-radiative, right?
Of course, yeah.
In plasma, you recombine by emitting electrons sometimes. Here, the only way to recombine is to have a third body, right? It should be a three-body recombination. If three stars find themselves by accident near each other, they can conspire to eject the third one and to form a tight binary between the two, right?
Yeah.
So these three-body recombinations happen, right? So this is the physics of it, indeed. But sorry, let me, because it's an interesting story, we will get back to it. But three-body recombination, of course, is very slow. Before three-body recombination will happen, however, you will start evaporating things from the system, right? Because for that, you only need to exchange energy. You don't need to form a tight binary. Yeah?
I was going to ask about evaporation, exactly.
Right. Evaporation happens first, tight binary is later. Because you can evaporate at the expense of all of them, right? Because in this binary collision, you do not form, if just two stars moving in a common gravitational potential collide, you obviously don't form a binary because you have been on this hyperbolic, you remain on the, but you do exchange energy. If you exchange energy such that the total energy of one of the outgoing stars happens to be positive, it will escape the cluster, okay? I'm not an expert in these clusters because you understand, for me, this is just an illustration, but this must be so. All right, so now we are done with this thing, why it doesn't work. Now let me show you why it does. Tremaine with collaborators, especially Tuma, realized that if you have a nuclear star cluster, nuclear here refers to the nucleus of the galaxy, some heavy mass here, then your individual stars will be on various elliptical orbits here. And then your fundamental object is no longer a Newtonian mass, say Tremaine and Tuma. Rather, it is a Keplerian ellipse. It's like in string theory, you replace a particle by a string and then you avoid singularity. No, quite literally actually, right? One of the claims to fame of string theory is that singularity is due to these Feynman diagrams, and we have seen this Feynman diagrams last time, right? It becomes fat and it's less singular. So in fact, replacing a particle by an ellipse allows you to remove this I equals to 0 singularity, okay? Now, what about I equals to infinity singularity? Again, so I'm assuming that the mass of the star cluster is much smaller than the black hole mass. Then to a very good accuracy, my primary objects are ellipses rather than particles. I smear my particle along this thing. Then I have interacting ellipses. The resulting system can be shown to be Hamiltonian. So I'm still using canonical equations of motion, but no longer for particles. The phase space becomes slightly different. It's the phase space of ellipses, okay? The equations of motion in the phase space of ellipses remains Hamiltonian. I can still use standard classical statistical mechanics.
So, Andrei,
So-
there is.
Yeah, go ahead.
So this confused me in Yuri's talk, which was if the relaxation time, like for the actual particles running around, is short compared to whatever process you want to follow in this situation, then this approximation breaks down, right?
So, if you have this black hole here, it is just another point Newtonian mass in my description. So if you look at the system and sit there long enough, it will relax to the standard canonical distribution, and therefore it will explode. The claim here is that ellipses relax faster than particles. Faster. Ellipses will change their orientations and stuff before the two particles will collide and the whole hell will break
And
loose.
that's independent of the number of these.
Because now you see in this hierarchy, now I have also this M, the mass of the black hole, which I assume to be much greater than the mass of the cluster. So I now have another small parameter in this problem, and the claim is that in this approximation, you will actually relax, ellipses will relax before particles.
Okay. When you say ellipses relax, you mean just the angular momentum can change, but their energies are.
Yeah, I will tell you. I'm about to tell what exactly happens to those ellipses. Because, okay, so I said I have removed I equals to 0 singularity by string theory. And what about the I equals to infinity singularity? Here is.
Are you averaging over time or?
Original time, of course, right. Right, exactly. So the relaxation time is way longer than the orbital time. This is the standard Malkovich thing, you know, this guy about warming and this equations of motion that are called Malkovich thing. Okay. Milankovich, whatever, right.
Markovich is John
Some syrup or something.
Okay, let's move on.
Okay, so there are these ellipses, right? Now, another important thing. Of course, you know from Kepler that t squared is a cubed, where a is the semi-major axis, right? We have already mentioned without proof that energy is a function of the semi-major axis only, okay? This means that the adiabatic invariant, which is energy over frequency, is a function of semi-major axis only. So for the ellipse, the adiabatic invariant, it's just like for pendulum, you know, right? If you have a pendulum, if I gradually move it up, its energy will change, but its adiabatic invariant will remain constant. In the case of those ellipses, it turns out that energy, period, and adiabatic invariant are functions of semi-major axis only. And so, if I only gradually change my potential in which those ellipses are moving, which is what I'm assuming, that the time scale of the evolution is much longer than one orbital time, then the ellipses will actually keep their semi-major axis. But semi-major axis is the only parameter which made the phase space infinite, because also energy is now kept constant. So it means that all my phase space for the ellipses all of a sudden has become compact. So my ellipse can evolve all the way from a circle to a degenerate ellipse of twice the radius because it keeps the semi-major axis. It can change all orientations, all right? But it will preserve, again, the semi-major axis. I'm now in a compact phase space.
But
So
there's
no
room.
infinity at infinity, yes.
Sorry,
No, go ahead.
sorry, but E over omega is the automatic invariant for the harmonic oscillator. But I think if you do it for the Keplerian orbits, it turns out to be a function of the eccentricity only.
No. The adiabatic invariant is all right. If you take energy over omega, it is, let me put it slightly differently. In fact, I was thinking about similar thing this very morning, and at some point I started to panic, and I thought, oh, I should call Levin. I wouldn't know this, but I think I got it right. Look at this energy thing, okay? So imagine that you have this potential in which my ellipse is now moving. So forget all other ellipses. Take just one ellipse, and my potential now is not just the black hole, but also some external perturbing, but time independent and weak potential. Because remember, I'm always dominated by the black hole. Then my energy will be constant because it is time independent potential. So what can happen to my ellipse in this external time independent potential? To keep its energy constant, it will have to preserve its semi-major axis.
Sorry, but he said if
So,
the external perturbation is time independent.
very good. So for a time independent external perturbation, you agree I keep my semi-major axis.
Well,
Simply because it is energy. I keep it to the extent of how large is my perturbation. If my perturbation is epsilon, my eccentricity, my semi-major axis will not be perturbed by more than epsilon %.
But neither will the orientation of eccentricity.
No. What are you talking about? All those things will gradually accumulate from orbit to orbit under the influence of all those. You will gradually migrate some way. Everything will change, but not A, because energy is constant. Think about it. We can talk afterwards. I'm right.
You're always right.
No, but really, I'm right here not for a good reason. That's because this is what Tremaine and Tuma are saying, not because I thought deeply enough. But I thought deep enough.
But Andrei, this model doesn't permit any evaporation. I mean, obviously.
Simply because I keep A constant.
But there is, indeed, there is evaporation from systems like this, is there not? Or is there really not?
Let's.
Does the black
So first of all, I don't know much
maybe
about.
not because of that approximation.
Not on this time scale.
Yeah,
Would be my answer. Okay, so because of that, you can do statistical mechanics of.
You can use another board.
No, I rather erase. So you can.
It is safer.
So you can do statistical mechanics of those things. It was mostly developed by, like I said already, Tuma Tremaine thermodynamics. Then Levin came to me and Jiarong saying that this is a very, very powerful tool. So now I'm talking about astrophysics. And we did some technical work here and developing this thermodynamics. But let me first briefly tell you about astro applications, because that's what drives the interest for this field indeed. Now, astrophysics, of course, in general, can be, is it fair? Astrophysics is look at everything you can see and try to understand everything you saw. Is it a good description?
Yeah, that's pretty much it.
I think it summarizes it fairly, right?
I'll accept.
So in this case, they look at these nuclear star clusters and they try to see what's happening there. Now, of course, this has some strange feeling here because whatever, Principia is 300 years old, so yet another confirmation of Newton doesn't sound like a good idea. Now, the standard, how to say it, the standard excuse here is, however, this is how we have discovered Neptune, GR deviations of Mercury, dark matter, right, by watching the galaxies move in a cluster of galaxies or by watching the rotation curves. Now, I don't think that Tuma, Tremaine, and Levin can claim equally spectacular discoveries with this technique, but they are kind of beautiful. Let me mention a few of them. So first of all, in M31, Andromeda. In Andromeda, they see a double nucleus. You can read about it, double nucleus in Andromeda. So you can say, okay, perhaps the galaxies merged, those are two nuclei. Then comes Tremaine and says, you see, in this Tuma-Tremaine thermodynamics, there are actually spontaneously broken states. There is a symmetry breaking similar like in magnetic material. There are thermodynamic states where ellipses want to be together. And then, says Tremaine, there are all those ellipses here. But if you have all those ellipses here, the velocity is the smallest near the apogee. What do you call it? Not in this case.
Or
this is not a G.
galacticon.
Epicenter.
Epicenter. Thank you. So the velocity is the smallest near the epicenter. And so if you remove my orbits and look at the actual stars, there will be some general fuzz, but a lot of them will be near their epicenters. Okay? Wonderful. So you don't need to adjust your cosmology to account for this W. Okay, the usual astrophysical story. It's useful to understand the world. Then comes Levin and he says, look, Levin's claim to fame here, which I didn't understand for a long time, but I think now I do, was what he called centrifuges. He says in his paper, he is a poetic type, of course, as you know. So in his paper, he says that these nuclear star clusters are giant centrifuges at the centers of the galaxies. When I read it first, I thought, what the centrifuges? So sure, they can rotate, but he meant centrifuges in a different sense. For him, a centrifuge is a separation device. Like you want to get rid of whatever, uranium-238, okay? So you put it into a centrifuge.
Or buttermilk.
Buttermilk. People have different priorities. So this is what Levin means, but even more down to earth. If you have some heavy gas, it will be near the bottom of the atmosphere. Okay, this is what he means. In thermodynamic equilibrium, heavier structures react more to this Boltzmann factor things. And so, says Levin, in this funny thing, there will be a lot of, if I put some stellar mass black holes, and most of my stars are just solar mass stars, then these black holes will concentrate where the Boltzmann factor tells them. They will be even more eccentric. And this is interesting, says Levin, for this future gravitational wave states. And he even more, in his recent paper, he says he gives totally crazy scenarios. For example, he says, if this nuclear star cluster is rotating, then it will, in fact, and if then you form a gaseous disk, this gaseous disk will act as a single very massive star, says Levin in his Flight of Imagination. So this very massive star, he says, will react to the Boltzmann factor so much that it will go totally into the plane of rotation. So he claims, let me finish the sentence, he claims that rotating nuclear star clusters will orient gaseous disks with their rotation. And then, since this disk will later be eaten up by the black hole mass, you will contribute the angular momentum along the direction of rotation of the nuclear star clusters. That's how you can get very fast spinning black holes, because all accretion episodes will be perfectly aligned by this centrifuge, if you wish. You have a question?
Are you going to tell us what's the actual Boltzmann factor? Because you just mentioned
What the actual what?
Boltzmann factor, when you just have this eccentric. What is E in this case? Because E is fixed for every.
E here is, yeah, I can tell you briefly, because I want to ask you to help me, not to tell you the story, but briefly, this is what's happening here. So this is what we have done with Jarong and Levin. We have said, okay, let me buy this idea that it is thermodynamics. Let me write the most general distribution here. Now, since it is long-range force, I of course will not do whatever 1,000 stars and compute the energy for all of them. I will use mean field approximation for long-range force. This should be perfectly adequate. And so I will say there is a general gravitational potential phi which comes from the masses of all ellipses. So given ellipses, I can compute the potential phi. Given this potential phi, for each ellipse in this external potential phi, I can compute the potential energy. Since kinetic energy is the adiabatic invariant together with this thing, well, this is all I need for the energy thing. So now then, the answer to your question, you will not like it. A star, or in this case an ellipse, is characterized by its mass, semi-major axis, eccentricity, and two unit vectors which are mutually perpendicular, which characterize the orientation of the ellipse, right? For ellipse, there are two things, okay? So this is your phase space. Now, those are, what do you call it, immutable characteristics or whatever, right? Those will not change. Combine them into parameter A. These guys will change as you evolve. And then I will say the following. These things are not evolving, so they can be arbitrarily distributed. These things are evolving, and so I will get a distribution function which is given by the distribution function which is given to me divided by this partition function e to minus beta u u is the potential energy of this ellipse in this given potential created by all other ellipses. J is the angular momentum of this ellipse. And of course, since total angular momentum is conserved, in addition to the usual inverse temperature, I have three more inverse temperatures describing conservation of the angular momentum.
So
all right?
Everything is at the exponent.
Yeah, everything is under the exponent. And z of a here is just the integral of this guy over dv. Okay? So this is what we have done with Jarong. Jarong was instrumental at that point I will mention in a sec. So let me, and then of course we solved this equation, right? Where rho is the density created by all those ellipses. The usual thing, right? So I have myself this nonlinear Boltzmann equation, highly nonlinear integral differential equations, whatever. So our achievement was that before us, Tremaine and Tuma were solving it with various simplifying assumptions. We have demonstrated that we can do it by brute force, because this phase space, even though large, is not infinitely large for a modern computer. We sampled this phase space, we populated. Basically, we did compute this multi-valued integral and solved this nonlinear Poisson-Boltzmann equation by iterations. Okay, and so we were able to trace the phase space of this statistical mechanics system, and this is what we found. And this will lead me to this question, which I cannot answer.
Sorry, this calculation is evolution, or this is just looking at the distribution
I did.
in equilibrium?
I did the following. So I literally was solving this equation by iterations, meaning the following. I start with an arbitrary potential, say 0, whatever. Given some potential, I have my distribution function in terms of the potential. So I populate my phase space according to this distribution function. Once I populate my phase space, I can compute the resulting rho. Once I have the rho, I can compute the resulting phi. But this was not the correct phi which created this rho, repeat, until converge.
Okay, so using a relaxation technique to solve.
Well, you can call it relaxation technique, but it's really like, suppose I'm solving this equation, x squared plus x equals 0.1. So in this case, relaxation technique will be this. And so on.
Right.
Right?
Yep.
How do you know that the solution is unique?
Oh, it's not. That's what I'm about to tell you, and that's where my troubles lie. And again, I think these troubles are serious enough, so I even consulted those knowledgeable people with with zero results so far. And at some point I thought I understand it, now I again think I don't understand it. So here's what we find. Take gamma equals to 0. This gamma was the temperature for angular momentum, so this is a non-rotating star cluster. Then this procedure, this will be my binding energy, right? Because all those ellipses interact, right? And so it will have some binding energy, and binding energy will be negative, total energy will be negative, so this is modulus of binding energy. This is my inverse temperature beta. In this case, of course, since I have compact phase space, my temperature can be negative. What's the problem, right? If I put your molecules here, all the molecules are down. But if I put an upper wall, I can make temperature negative, they will be all up, right? No problem. So for a compact space, my temperature can be negative. We find a lot of spherically symmetrical solutions. Here by spherically symmetrical solutions, I mean that the resulting gravitational potential is spherically symmetrical. However, the stars here are this hedgehog. Because for negative temperature, they want to have as small potential energy as possible. So they fly away from each other, but preserving semi-major axis. Okay, hedgehog. Here, all of them are circles. They want to be as down as possible, so those are all circular orbits. So this is spherical.
And by spherical, you really mean the
I find the solution of the Poisson equation that I find is characterized by spherical symmetrical gravitational potential. Then I find, since it is finite resolution, I don't have infinite energies, but in fact there is this branch which is called degenerate, formally corresponding to infinite energy. How do I know to infinite energy? Because as I increase the resolution, it becomes larger and larger and larger, this binding energy. And the stars here look like this. These are all the fully degenerate ellipses which lie totally on top of each other. And I find that within the same numerical scheme, you understand. And then I also have this branch, which is broken symmetry, non-spherically symmetrical, and here they look like this, only they are non-degenerate. These guys look exactly or similar to M31, okay? So how can we understand this phase space? Here is where Jarong was instrumental, because for whatever reason I did not see it with my own eyes. For this degenerate branch, here is the little problem for you. If you have a rod, uniform density rod, and another uniform density rod which you put on top of it, what will be the gravitational binding energy? The answer is it will be infinite. For some reason I didn't see it myself. The answer is infinite because this integral, of course, diverges logarithmically. Right? If you have x1, x2, the distance between them, density, since it is a linear arrangement, masses are dx1, dx2. This is the distance between them. So this thing diverges logarithmically, okay? Now, and logarithm is a very interesting, what do I mean diverges logarithmically? It means that if I take these ellipses, which are not totally aligned, then this thing will be over the log theta. If I take ellipses which don't have totally eccentricity 1, then I will have log 1 over 1 minus eccentricity, okay? Logarithmic divergence. But logarithmic divergence in statistical mechanics with canonical distribution is very, very special, because the penalty for having small angle in phase space is over the theta squared. The advantage in energy is this. Boom, boom. Beta critical is 2. That is to say, if I have systems with logarithmic interactions, I get myself a critical temperature such that below this critical temperature, my partition function will diverge. And undoubtedly, this is exactly what happens here. Now, that's fine. So sure, I mean, this is even physically obvious, right? If you have, suppose I want, think in terms of microcanonical distribution. Then you just put a system with a fixed energy. Suppose I want a lot of energy, a lot of binding energy. How can I achieve a lot of binding energy? I make all my ellipses degenerate and I put them on top of each other. So clearly, this corner of phase space should be populated, no problemo. The question is,
And you get a double nucleus.
and you, no, here it will be too much of a double nucleus, right? It will be like bright, right? This is the double nucleus. So we do have broken symmetry states which are non-degenerate, and this is double nucleus. This thing, but my problem. So now I have 10 minutes for myself. I get to ask my question here. This is my problem, that for this temperature beta, inverse temperature beta, these guys and these guys and these guys, who cares, maybe they are unstable, whatever. But these two guys coexist. It means that a perfectly legitimate state, which supposedly describes this double nucleus, if instead of doing mean field theory, solving this Poisson equation, I actually put this million stars or whatever, 100,000 stars on their ellipses and try to do honest to God statistical mechanics of it, I will discover that for this temperature, my partition function diverges. This is no good, right? I mean, you try to become, right? Because if instead of mean field theory, you are doing the full partition function, you should get better results, whatever, more accurate results, stuff like that. But this is not what, so here I have, so the question then, which I want to ask you is this. Does this temperature even make sense? Right, because it certainly does not make sense in the rigorist sense of the word, because rigorist would say, let me compute the partition function, everything follows. But partition function for this temperature diverges, this I know because of those things, because of this Jarong thing. Okay? Partition function diverges. Does this temperature make sense? So I thought,
Is it always true that if the partition function diverges,
I
you
have
can't
no-
do anything?
like I
Because
said-
I think,
like I said,
aren't there cases where you can, there's infinite number of,
I have no clue, Mike. That's the problem. Especially, this is a very simple system, and I can further simplify it for so-called Kirchhoff vortices, which have logarithmic interactions. And so, if some of you is interested, I can tell him about this Kirchhoff vortice, because, well, clearly the heart of the problem is in this logarithm. So I invented an artificial system of point vortices on the surface of a sphere, which is a Hamiltonian system, which demonstrates the same thing. My spontaneous symmetry breaking occurs at a temperature at which my full partition function actually diverges. So let me explain why for a while because our paper with Jarong is like 3 years old, and I more or less knew but I somehow because brain is a funny thing, right? You can convince yourself in almost anything, right? So I convinced myself that this is not a problem. How? Because I said, oh, you see, this is such a tiny, tiny corner of the phase space. Maybe I never go there. Maybe I just happily stay here. So the temperature is a perfect descriptor of what my stars are doing if you don't go too close to this highly, highly degenerate thing. So my kind of excuse for myself was this, that if I actually arrange this microcanonical distribution with the corresponding binding energy, it will there will be no penalties for that or whatever, okay? Because you understand, microcanonical distribution is absolutely okay here. I have a compact phase space, right? The only way to destroy microcanonical distribution is to have non-compact phase space. So that is to say, if I put my rod, my ellipses with the binding energy equal to this, right? It will have to relax into something. And I was telling myself it will relax exactly into this point, okay? Okay? But on the other hand, if normally, normally, it doesn't matter which distribution you use, microcanonical or canonical, the microcanonical will always end up being canonical distribution with a certain beta, okay? So, but now I don't believe this escape anymore, because the problem with this argument, how to say, the problem with my explanation that this is a tiny corner of the phase space is as follows. Look at this result. This result says that my partition function behaves as theta to the power 2 minus beta. So even if my theta is large, even for large theta, I still have the tendency for this thing to collapse, okay? So it's not a tiny, there will be some attractor, non-trivial, that's because if there was no attractor, my numerical program will never find this thing. So there is some attractor for these degenerate states. And so, here am I. I know that my temperature cannot be applied literally, and yet it does seem that if I run it on my computer, the resulting distribution will be something like this. So instead of running ellipses, which is very complicated, because back to your question, I cheated, of course. I said it's an energy in a given potential, which I compute using this distribution. But those are incalculable integrals, of course, so we have to do it numerically, whatever. But for this point vortices is on the surface of a sphere with logarithmic interactions, I can run it on my computer, and so I'm planning actually to run it. And so, so far nobody told me that this is meaningless, so I will have to run it. Maybe one of you can be interested in running this too, and run it without telling me, and then we compare, whatever. Okay, so this is all I wanted to say.
We have further, Stefan has a.
So if you turn on the gamma, the chemical potential for the angular momentum, does it help to regulate the divergence?
No, because this thing doesn't have any degeneracies, right? So in fact, even though according to Tremaine, introducing this gamma and mapping a large whatever, a lot of this phase space was the main achievement of our paper or whatever, because he was doing it case by case. We did it like in full generality. My interest, it does not change anything about this degeneracy, right? The degeneracy is just this, okay? So there is this strange, and literally think about it, like put some vortices on a sphere. Doesn't matter what is a vortex, it's something which follows Hamiltonian dynamics. These guys interact by logarithmic potential, modified correspondingly to account for spherical symmetry, of course. So this guy, now, if all these guys are, because I want to stress this, that the problem is absolutely trivial, almost trivial, because if all these guys gather together, there is a lot of binding energy. So much so that certain temperatures lead to divergent partition functions. And yet, at those same temperatures, other equilibria exist. My question is actually very, very simple. Those other equilibria, in what sense are they characterized by a temperature? Because it cannot be let me show you one little thing here, which is kind of beautiful and illustrates the problem very well.
But the degenerate state has zero angular momentum. All ellipses with zero angular momentum.
They are not, no, because the angular momentum here is also a function of just the shape of the ellipse, right?
Oh, but if it's
So it
a
simply
rod-
means that ellipse oriented like so and ellipse oriented like so have exactly the same energy.
Do I understand correctly that they're like ellipses with
If they are totally elongated, they have zero angular momentum, of course, right?
But this is what you call the degenerate state or not?
Degenerate ellipse is an ellipse with zero inclusivity and therefore with zero angular momentum, yes.
Right.
But it has nothing to do with what you, because
How do you get to that angle?
take this ellipse, then it will have some angular momentum,
Yeah.
but it's not the singularity, however, is not in the angular momentum, right? Angular momentum simply tells you that going this way and going this way have different weights. But the singularity in the potential, this logarithmic singularity, comes just from the gravitational interaction, not from the direction in which you orbit.
I guess my question is that if you say I do have a fixed angular momentum, can you ever get this degenerate state which has zero angular
Oh,
momentum?
if you go into microcanonical with this, yeah, you will probably you will have to dump much of your angular momentum to some circles and let the others become degenerate. It will modify your phase space, but it will not exclude the problem, since the problem already once again, maybe I'm thinking too much, but I want to address this problem of theoretical physics. What does it mean to have a microcanonical distribution with a divergent canonical partition function? And in what sense this temperature is even a temperature? So let me take 1 minute. I'm sure you will like this thing. Back to globular clusters. We know here that partition function diverges on two ends, okay? But let me say, oh, the hell with it. Let me do it by mean field theory. Now you see, if I do it by mean field theory, right, this is the concentration in a given potential, right, of stars. This is my potential, density, so this is my Poisson equation. You see, now I have removed the divergence near the center. And in fact, think about it. If 3 body collisions did not happen yet, but 2 body collisions have happened, maybe indeed this divergence will be irrelevant, whatever. Now, still I will be diverging at large r, right? Because at r going to infinity, phi goes to 0, so I'll have finite density here, but let me do this. In fact, some such thing is what they call king profile in globular clusters, whatever. But back to my...
I think there's a -1.
There is a -1 here, so as to make this transition not sharp, right? They call it king profile now, and it claims that it kind of works, whatever. But then there are other problems which have nothing to do with Mr. Boltzmann, okay? And they work equally well, I think, whatever. But what is the meaning of this beta? Normally, this temperature is the same thing you use if I want now to ask, not about the mean profile, but I want to ask, what is the probability that 2 stars in a cluster are at a small distance r from each other? If I was in the normal realm of classical statistical mechanics, the probability would be E2 minus beta minus 1 over r. And here, of course, it's not, because this thing would diverge. So this is again my question. So the question has some very practical component to it. What exactly is the meaning of this beta? This certainly does not correctly describe the 2-point function of the stars in the globular cluster, even if it does describe the mean potential. So it is some kind of a, and I feel so powerless that the only thing I can propose is to run point vortices on a sphere on my computer, watch it as a stupid monkey, and hope that I will see something. Okay?
Let's thank Andrei again. There should be cookies and stuff. What? It's a hydrogen atom. Has a whole bunch of, it has an infinite number of states you can read.
Yeah.
So it doesn't, it's partition function. I thought there was this problem with an isolated hydrogen atom that like actually like had infinite space, finite energy, and that seemed problematic.
Yeah, because if you sum all the way to n equals infinity.
Yeah, but which obviously never.
Oh, in this case,
Yeah,
because we are
Yeah, because it's
there's always something.
we don't never assume we don't assume equilibrium.
Right,
So if
yeah,
you do
yeah.
assume a relative equilibrium rather than
My point is that it's very rare that it happens.
Yeah.
But nobody seems to worry about that problem in
don't
that.
have any chemical potential.
Anyway.
And when it has
You can describe the number of particles.
In practice.
After I said, let's meet on
Put some
Monday,
initial sign and
I'm
solve
sprint. I'm actually
Into
just
your partition function, you admit
And back and
multiple
forth,
number
yeah,
of particles
back
into your
and forth,
system.
yeah.
You're not considering.
I thought he had to But I don't know, what I don't understand is, does it mean that there are some energies? Oh, no, maybe you're right, maybe it
So you say like
evolves.
if curly phi starts from 0, for example, and then you have the
Okay,
solution.
yeah, so,
And then give it
yeah, so maybe just, maybe there's some separation where
Yeah.
So,
you end up in one or the other.
can you write, I have a piece of paper, can you write, oh, by the way, Marcus, where is Marcus? So you can ask Marcus about what, have you organized this? Oh, you have done it.
Yeah, whatever, yeah.
Okay, good. So,
Send me an email
No,
just
fine.
saying, let's meet at the Monday, just because that's what I check the calendar. Good, great.
So, can you please then notify Lorelei that you will be organizing student hour for spring? Okay?
When is it?
It's between 2:30 and 3:30. Oh, week, sorry, it's it is February 16th. Okay? Thank you.
Could the infinite in partial just have like since you have when you have like n-body problem exists, it's eventually everything will
Say again. Oh, they rarely call the end, but you see. No, but let me explain. My approach here is this. Once I have encountered this problem, okay, I want to make sense out of it. The simplest way to make sense out of it is to forget about the initial motivation. Exactly. Just forget the initial motivation. You have a you have a well-defined Hamiltonian system with compact phase space, which demonstrates this phenomenon that at a certain temperature beta, your partition function diverges. This I can prove rigorously because of this Jerome ellipsis. Okay. On the other hand, at the same temperature beta, if I attempt to solve it in a mean field theory, which of course should be perfect for this long-range system, I do get another solution too. Okay? Now I'm asking my question, what the hell does this temperature beta mean? Because I have no doubt that if I do a microcanonical thing with the energy given, because you understand how it works, right? Normally, how to say it, original physics problem is of course microcanonical distribution. Like if you take molecules in this room with perfectly reflecting walls, it will keep the energy.
Right.
But of course we know that in normal physics, it doesn't matter microcanonical or canonical, there will still be some resulting temperature, right? And this will perfectly describe various collections of stars, 2-point, 3-point, 4-point, whatever point correlation functions, correct?
Sure.
In this case, however, it does not seem to be this way, because this is my binding energy, this is my temperature, inverse temperature rather. I have this degenerate thing with infinite binding energy, and I have this symmetry broken thing with a finite binding energy. So now I'm asking you this, I put this system, a system with this energy into my box, okay? And with zero total angular momentum, which is of course very easy to achieve. To each ellipse like so, I add ellipse like so. So zero total angular momentum has nothing to do with it. Put this system with this energy into a container and wait. I have very little doubt that I will discover the resulting psi distribution exactly given by the symmetry broken state with exactly this temperature.
Sure.
Again, besides, when I say I have no doubt, it doesn't mean that I have done it. I have no doubt. But I will do it. I will find this.
Right.
So it means that this temperature and this state does make perfect sense. Yet, if you compute the partition function at this inverse temperature, you will get an infinity, because this state, which exists at the same temperature of this degenerate ellipsis, will take most of the phase space.
There is no question of stability. I mean,
so I don't know. This is exactly what I'm asking. So this means formally that my temperature beta cannot be the usual full-fledged temperature, in the sense that it does not describe arbitrarily large collections of stars. Like, for example, it does not describe how my system behaves in this funny, you see? So I don't know what will be the penalty for having this point over here. So once again, my statement is this. This is a funny temperature in the sense that I cannot use it to describe two large collections of stars. Like, if I ask about n-point correlation function, where n is the number of stars, this beta will give me a false prediction that I'm here.
It's not good when your temperature becomes extensive.
So right. No. It's not that it becomes extensive. It's just that certain states are certainly not described by this temperature. Right? This temperature perhaps is working nicely in the neighborhood of this point, whatever it means. But this is exactly what I want to understand. I want to understand what is the precise meaning of this temperature if my partition function actually diverges. Yeah. And you understand, those are not divergences of some quantum theory or whatever. This is just simple classical physics.
Right. It's like all of the things that I want to say that might like help address something are related to the stars and not to these ellipses as like platonic objects.
Exactly.
Right. It's like, oh, what if the semi-major axes actually do change because, you know,
because of some additional effects,
order of epsilon.
Exactly. But this is not what I'm asking.
No, no, that's fascinating.
Then couldn't it have to do with evaporation?
But there is no evaporation.
There is no evaporation. My phase space is compact. Remember, this is what we started with. I want to figure out this classical physics problem. I have this Hamiltonian with compact phase space, with divergent partition function, and yet within the framework of the mean field theory, I have a nice looking solution.
But when you do this numerically, you do.
I have not done it yet, so.
And
I will do it only for point vortices, but I have invented point vortices which demonstrate the same phenomenon.
But they don't have
for point
evaporation.
vortices, right? There is a famous modeling, Kosterlitz-Orles model in 2 dimensions, where you have vortices that interact.
But my vortices actually have to be slightly different. Namely, I have to put them on a sphere. Moreover, I have to insist. Moreover, they have to be quadrupole vortices, plus with neutralizing background here. Okay, because you cannot have two pluses, as you know, right?
And so you don't want to neutralize them with minuses, with minus vortices.
Minuses I smear. Only in this situation of this funny quadrupole vortices, I can demonstrate analytically that the symmetry breaking temperature is actually below this temperature where my partition function diverges. So in this situation, because again, then I can say, suppose you consider a collection like this, right? Because they are all diametrically opposite to each other, these quadrupole vortices. And you let them do their thing, move around. They are similar indeed to those vortices with logarithmic potential, everything. So they will do their dance, and in the mean field, I will be here. But I will be here at a temperature such that at this temperature, my microcanonical distribution predicts that I should collapse all of them.
So the strange thing is that they coexist at the same beta. There is no
exactly. That's why I needed to invent this quadrupole vortices, because if it is just normal vortices, then in fact the degenerate thing becomes part of the family of symmetry broken solutions.
So you have one
situation
in one case, then you raise the temperature, and then
exactly. As you gradually rise the temperature, you go more and more degenerate, and at a certain temperature you go fully degenerate, no problem. Here, however, with this quadrupolar things, I'm in a different situation. Where once any broken symmetry state requires a temperature such that at this temperature my full partition function diverges.
Can I ask you a simplified version of your problem? So, if you take, let's say, a single, this is fixed, so the center is fixed, and you look at the thermodynamics of a single star. You say, okay, let me now put this system at some temperature T. What do you get?
Star treated, you mean treated in the ellipse approximation or what?
I don't know. There's simply a 1/r potential connecting it to.
Oh, this thing is okay, right? In this case, you have microcanonical partition function which converges while canonical diverges.
You're saying the canonical partition function diverges here?
Yeah, trivially so, right? Because it will be, you can always go to the center of mass, then your phase space is just d3r, d3v, e2 minus beta minus 1/r plus v squared over 2.
Yeah.
So this thing diverges both at 0 and at infinity.
Okay, and now, because for instance,
Microcanonical will converge because the ellipse is finite.
well, in microcanonical, there's nothing to do. No?
Exactly. In the microcanonical, exactly. You give already the semi-major axis of the ellipse, and there is only a finite phase space of ellipses with a given semi-major axis.
But for instance, in field theory, the partition function diverges all the time, and still when we normalize by the partition function, when we compute average quantities, like, I don't know, the average energy.
Yeah, but there you are dealing with all this ultraviolet and whatever things. There quantum mechanics saves you, or something. Right here it's very different, right? Those are just real states you can enumerate. Moreover, in this problem, the divergence of the partition function is real.
It's real.
It's
so
described.
Compute the average energy is minus infinity somehow.
Right. It describes what actually happens. Right. If you wait long enough, you will form these binaries with arbitrarily small separation. It's like this. But this is kind of interesting and something which we don't talk much about. It's related to this fact that classical plasma does not exist. If you take classical plasma, non-quantum, it will recombine for the same reason, right? Electrons will sit right on top of there, of course, you know de Broglie saves us. But here I don't have no de Broglie, right? These are stars.
Or black holes.
Or black holes, right, whatever. So yeah, but again, I'm not waiting long enough for the true relaxation to happen.
But so what is the n for this thing to work? So if you apply to the solar
10
system.
to 4, 10 to 5.
Okay, so solar system is
there will be all these resonances, individual resonances, which will dominate the dynamic, right? Hence all these crazy trochons, whatever, you know, all these asteroids. Yeah, okay.
So it's the coexistence, right? Because if the partition function diverges at one temperature,
it's not
fine,
wrong,
it's
right.
a phase transition. But the fact that you have these two coexisting phases
At the same temperature.
At the same temperature.
This kind of seems to invalidate the meaning of this temperature at some level necessarily.
I mean, in Kosterlitz-Taules, which is vortices with logarithmic interactions, but I mean, balancing vortices at low temperature, you know, they do one thing, at a high they do another, and so you have two phases, and then no coexisting phase.
Quindi quella conclusione è che non normalizza, in un sistema di stelle non normalizza.
Cioè, perché non sa come interpretarlo. Se fosse
problem too, I guess.
Oh, so they already asked you about,
Yeah, yeah,
okay,
yeah.
okay, so then they.
Yeah, and on this application, I would just maybe do this double product which you said and cover some metrics.